almost here. OK, so let me start by writing this is the type of equation I'm going to look at. And to write the or Hamilton-Jacobi equation. So either I looked at the PD ut equals h xt ux, subject to some initial condition, ux0 equals u0x, or the differentiated version of this, which means you differentiate both sides with respect to x and set ux equals rho. So the other equation would be rho t equals h x t rho, the whole thing differentiated with respect to x with some initial condition. So this is the kind of equation I'm interested in. And the focus would be in dimension 1. So here, first, maybe I should mention that rho here is ux. Here, x is an or, and t is non-negative. And h x t p, this is the flux or the Hamiltonian. That's the way to think about it. And the focus would be when either rho 0 or h or both are random. Now, let me before I state the type of results you can have for this equation, let me give a short review of, we'll call this equation 1, of the feature of the behavior of solutions to the equation 1. So that would allow me to motivate some of the results I'm going to say. Okay. For simplicity, assume hxtp depends on p only, and h is convex. Okay, so now the equation that I'm looking at would be rho t equals h rho x, which can be written as h prime of rho x, and this has some initial condition. So as is well known, this PDE has no classical solutions in general. So in general, no classical solution, even when rho 0 is smooth. And the type of discontinuities you would have because of the convexity takes the following form. So if rho xt is discontinuous at a location, say x equals xt. So maybe I should draw a picture. So imagine this is what you are seeing at time t. So you have some profile, some solution that looks like this. If you see something like this, and if you look at one of the discontinuity, with time, this location is going to change, And let's write rho minus for the value on the left and rho plus for the value on the right. In other words, rho minus is really rho evaluated at xt. You evaluate it from the left at time t. And rho plus, it's rho xt plus t. If you look at this, then the fact that, OK, so there is no classical solution, but you may write this in some weak sense. The fact that rho is a solution, is a weak solution to this equation, would force an ODE for the location of xt in terms of the left and right value. And the ODE would say that the speed of the location of the discontinuity would be negative h rho minus rho plus, where h rho minus rho plus is this ratio. So again, why this is an ODE? Because rho minus rho plus is really itself functions of the location. That's why when you write this down, you would have an ODE to solve. So that just follows from the fact that rho is a weak solution to this equation. That's basically, you can think of some kind of conservation law, and the conservation law would force that equation for the location of the discontinuity. However, again, it's known, well known, that the weak solution in general is not unique, so you have to put additional condition that often you find by adding some second order term, small viscosity, and sending the viscosity to 0. And moreover, we will have a unique solution if we require the entropy condition, which in our case, since H is convex, it really means that the left value must be less than the right value. So the picture that I draw purposely does satisfy that condition. So if it does discontinuity occurs, the left value must be less than the right value. So that gives you a quick review of the behavior of the solution. So let me make a remark here. Remark 1. So 2 remarks. One is that if initially you start with a function that has the so-called wrong type of discontinuity, that discontinuity should disappear, because that would cannot survive by the entropy condition. So maybe I call this entropy. Yeah, the entropy condition. So the first remark says that if rho 0, the initial density or initial profile, has a discontinuity with rho minus bigger than rho plus, then this would not survive as a discontinuity, and so-called rarefaction wave would form. So what it really means is this, that if initially you start with the wrong type of discontinuity, something like this, so this is at time t equals 0. This is rho minus rho plus. So what happens is that because of the very form of this equation, namely for rho constant, this is like a transport, it basically says that the density moves along the characteristic when minus h prime would be the characteristic speed. And since minus h prime is characteristic speed and h is convex, which means h prime is a decreasing function, so what happens is that this part travels with a speed which is different from the speed of the other part, and the speed is in such a way that the speed on the right is bigger than the left, so they kind of move apart. So the kind of picture you would get at later time would look like this, which means there is a gap to be filled here. And this gap, in fact, comes from a very standard solution to this PDE, which is of the form taking the derivative of h and taking the inverse and translate it and scale it. So somehow you insert this piece of the solution in between that would take care of the discontinuity. Now you have a continuous profile. So that's one remark to keep in mind. The second remark is that something that would be very typical in this business is that you may have different shock discontinuities, and different shocks may merge to each other and form the so-called stronger shocks. So this is a very common phenomenon. So what's happening is that the shock may be disappeared. So we may have no discontinuity at time t equals 0. At later on, you have various discontinuities. And then they travel with certain speeds given by this equation. But then the different shocks may run into each other and form kind of the number of shocks may decrease. So you may have, so if I draw a picture for kind of the location of discontinuities. So you have space and time. So let's say this curve would be one shock discontinuity. So this is, I'm plotting the graph of the shock discontinuity, this curve that satisfies this ODE. And then you may have another one. They may run into each other. Then they may form a stronger discontinuity. So let's say that the density on the left of this shock is rho minus. Here is rho plus star. Here, the discontinuity on this side would be rho plus. On the left would be rho minus star. So suppose you have a scenario like this. But then when they merge, then you have rho minus and rho plus. So somehow the kind of density information you have between these shocks disappears. So in some sense, what's happening is that the kind of solution you're forming here may lose information. In other words, if I'm here and I want to know what happened in the past, when I go back along the shock, then I don't know when and where to branch into different shocks. So shock discontinuities. So again, this is called shock discontinuity. May merge to form the so-called stronger shocks. Why stronger shocks? Because the first condition is rho minus is less than rho star plus. This is the shock discontinuity for the first discontinuity. The second would be rho minus star less than rho plus. So if when you arrive here, so you have rho minus less than this, and this less than that. When they combine, then you have rho minus rho plus. So it's as if you have a smaller shock. And by size of the shock, what I mean is the difference of these two densities and distance of these two densities. So these differences would add up and form a stronger shock discontinuity. That's the way to think about it. That's the intuition. And perhaps I should mention that maybe I stated as the third remark, which is very much related to the second remark. If T rho 0 at x is rho xt, so think of solving this differential equation as producing this nonlinear operator that would give you a profile at time t given the initial data. Then this operator somehow is compact in some sense. I.e., there is a gain in regularity So as I mentioned, if you solve a smooth solution, you may develop discontinuity. But if you look at it differently, in fact, there's some gain in the regularity of the solution if you assume H is, for example, nonlinear, when H is nonlinear. In some sense, as we go from rho 0 to TT rho 0, some information is lost. Okay, so this is just some general review for scalar conservation law. So now I want to give you an overview of some of the results we know about this PDE when, for example, the solution is a stochastic. So far, so good. Okay, so general thing. In some cases, as we start with a random initial data, then the random solution, the law of the random solution has, so it's kind of, you can have a closed equation and satisfies a certain closed equation. So that would be the general theme that I want to discuss for this lecture. Okay, so let's have some, here is a list of some classical results. Okay, so let me mention that the first example of scalar conservation law that was studied thoroughly was Berger's equation. And what Berger had in mind was that when H is quadratic function, then you may regard the so-called Berger's equation as a model of turbulence, provided the initial condition is random, like white noise. So I'm going to first consider the case H of P equals 1/2 of P squared, the celebrated Berger's equation. And it was observed by, well, I guess I better spell the names correctly, especially since all the authors are French. And I don't want to, let's see if I have some references here. I used to remember names much better than before. Kind of, oh yeah, Duchon, yes. Observed by Duchon, Carraro, and I think Chabot, that if rho 0 in the equation, the initial data in the equation rho t equals 1/2 rho squared x, or rho x, is a Leve process. Like, for example, you can take it to be Brownian motion. then this persists at later times, i.e. x going to rho xt, it's again a Leve process. And we can have an explicit, and we can derive a precise equation for the so-called Leve exponent. Measure, or even the corresponding Leve measure. Okay, so that was observed. In fact, what they did, they constructed something called a statistical solution to the equation, which is exactly behaves in this way. Though this statistical solution was a little bit strange. For one thing, it was not known whether the so-called statistical solution would coincide with entropy solution. And then later, Berkeley observed that, in fact, in general, that is not the case. And so it was not clear what they constructed is what we want. But then later, Berkeley proved that indeed this is also true for the entropy solution. So later, Berkeley proved that this is indeed the case for the entropy solution. Okay, so let me say this as a theorem now. So this is Berkeley. Okay, assume rho 0x equals to 0 for x negative and a Leve process. X bigger than 0, Leve process starting from 0. So I mean, if I want to draw the picture for Brownian motion, it would look like this. So this is rho 0. So let's say initially you have 0 here, and you start with something like a Brownian motion. Or maybe you allow once in a while a jump. However, it turns out that in this business, you don't want to deal with rarefaction wave. So I'm going to assume that, moreover, rho 0x has only the so-called positive jumps, i.e., if rho 0 is discontinuous, then rho 0 at some point A, then rho 0 A minus is just strictly less than rho 0 A plus. So suppose that is the situation. So it turns out that in this business, you want to stay away from rarefaction waves. And we know that they disappear immediately. But somehow, if I have some kind of Markovian randomness, if I allow rarefaction waves, then later on, I would have all these deterministic pieces that they look like the inverse of H prime, the so-called the derivative of the Lagrange transform. I mean, you want a Lagrange transform of H, and you want to avoid that. Okay? Then, if you look at the solution at later time, and look at the solution on the left of the origin, then the process x going to rho xt minus rho 0t. So this is the increment on the right of the origin for x positive. So if you look at the solution, the increment of the solution on the right of the origin at time t is also a Levy process. Moreover, you have a very precise formula for the so-called Leve exponent. Moreover, if you look at E rho xt minus rho 0t, and you multiply by a parameter, say s, minus, take the expected value of this. You have a random guy. So Levy process, since you're dealing with Levy random variables, you want to kind of look at its characteristic function. And you hope that you have some explicit formula. So the fact that this is Levy, it says that the characteristic function would be exponential, and the exponent should be linear in x. That has to do with the fact that the increments of Levy process is stationary. So you would have e times e of x times a suitable factor that would depend on time and s. So it would be a suitable nonlinear function of x, s, and time. And what was surprising is that you can derive a very precise formula for this exponent. See, for Levy process, if I know what the exponent is, then I know what the process is. If I know I have a Levy process, all I need to know is that what is the characteristic. And you can derive a very precise formula for the characteristic. Namely, if you differentiate the characteristic with respect to time, then you get psi times the derivative of psi with respect to s. In other words, psi solves a Berger's equation as well. And so you get, again, a Berger's equation for the exponent of the corresponding Levy process. And of course, if initially I know what Levy process I have, then this psi at t equals 0 is known. So I know what the initial data is. Then I solve this for later time. That would tell me what the Levy exponent is, and therefore that determines the process. And that was Bertoine's theorem. So let me make some. Not really. This is complex value solution. In fact, it turns out that you're looking for the smooth solution to this guy. So it would be like the solution using the method of characteristics. No, this is true globally. If the initial data is smooth, then it stays smooth here with the method of characteristics in this case. And in fact, I'm going to derive another equation, then that equation doesn't involve any Berger's equation, then you don't have to worry about it. It turns out that you can turn this to an equation for the corresponding Levy measure. So this is a complex value solution. You turn it to an equation for the Levy measure, and the Levy measure satisfies something which is a Smolov-Hofsky equation. And that is an ODE for which you don't have to worry about entropy or non-entropy solution. So let me make some remarks about this theorem. Why this theorem is rather surprising in the beginning. It may appear rather strange theorem. There is no reason to believe that you can derive a closed equation for the law of the process. So why this is surprising? The initial condition is the Levy exponent of the initial data. So initially it's solved with a Levy process for which the law is determined, therefore psi is determined. So this subject, okay, so so the initial condition is the Leve exponent of rho 0 x positive. So initially, I know what Levy process I have. Therefore, I know what psi is. Solve that equation, then that determines psi at later times. Then once you know what psi is, then the process is determined. So why is this? This is surprising. Let me make remarks. Somehow it's surprising. As I mentioned before, you lose information. So you start with a Markov process. Markov means that, if once in a while I refresh the process without looking at the past, and then you apply this nonlinear operator that will produce a random process that, of course, I can kind of go back to the initial data and determine what I have at later time by going back to the initial data using the method of characteristics. But the problem is, when you have shock discontinuities, some information is lost. So at later time, you have this nonlinear function of a Markov process. A priori, there is no reason that at later time you still have a Markov process because of the loss of the information. Nonetheless, you get a Markov process, and you can derive a very precise equation for this law. So as we mentioned before, some information is lost. Yes? OK, so what I mean is a Leve process is not just stable, meaning that I have a very precise formula for the Leve measure or not. But however, here, I have to make, I'm not stating all the conditions. First, I have to assume that, so somehow I have to make an assumption on the exponent. So I have to put some condition on the measure so that things don't blow up at data times. Okay? And also, what happens at later time here, you get a process. Let's see, what's the best way to say this? It's not stable in general. It could be a general. Yeah, but you need some regularity on the measure. There's some kind of integral equation you have to put on the measure. So I'm not stating everything. Maybe I stated in as a part of the remarks. So it's lost as we go from rho 0 to rho t. Nonetheless, rho t x going to rho xt is a Markov process. And we have a closed equation for its law. Okay, so the second remark I want to make is that the positivity of? Yes, it's very essential. Otherwise, this theorem is not correct. Because at later time, you have all this deterministic thing inserted in between, and that kind of mess up the Markov property. Yeah, that's very essential. So based on your questions, I'm kind of adding more and more remarks. Here, the positivity of jumps cannot be dropped. And the third one, I want to say that I forgot what I want to say. I think this jet lag is still there. OK, yes, there's an assumption. We need to assume, before I forget, I'm going to put 4 here, because I have several remarks. I've just I cannot control them. We need to assume that, for example, initially, if you look at the expected value of rho 0 at position 1, for example, you see the Leve measure may not be, Leve measure, it tells you with what rate you make a jump. That measure could have infinite first moment, and therefore it's possible that you make a lot of jumps going up. But then in between, I want to go down so that I don't have a blow up in finite time. Time here is a position, really. So you see, so the kind of solution that I have in mind is that you go down and you make a jump. You go down, you make a jump, so on and so forth. But if you don't go down, you just make a jump, these jumps could be overwhelming and would make the expected value infinite. So to avoid this, I'm going to assume this is negative. Okay? Though this may be dropped if we modify the statement. So the fourth comment, if that's right, exactly. You can have it exactly. If you add a drift so there must be a drift there to kind of pull it down. Otherwise, at 1, you may have infinity. That's right. OK, the other condition is that if rho nu t dx is the corresponding Leve measure, which has to do with the law of the jumps, then this itself, in this case, satisfies a differential equation. Then we can derive an equation for this measure. That somehow it has the flavor of kinetic equation. So this somehow tells you that, maybe I call it d rho, maybe dz. This basically says that if you're at state rho minus for the value on the left of the shock, then you make a random jump and you go to rho plus. And let's write z for the size of the jump, meaning rho plus is rho minus plus z. So this really tells you with what rate you jump from rho minus to rho minus plus z. Then this measure itself satisfies an equation, and it has a flavor of a kinetic equation, because what's happening is that if you have 2 different shocks, then these shocks travels and they may run into each other and they combine, and you have a new shock for which the size is the sum of the previous shocks. So remember that if you have these 2 discontinuities, they merge, then they combine, then the difference between left and right is the sum of the differences before. And this reminds us of Smoluchowski equation. When you have clusters of different sizes, they merge and they form a larger cluster, when the size of the new cluster is the sum of the previous ones. So this measure solves a Smoluchowski type equation. Here, z represents the size of the jump, and as 2 shocks meet, we get of jump sizes z1 and z2, we get a new shock of jump size z1 plus z2. So all I'm saying is that if you have, let's say, a jump size z1 here, a jump size z2 here, of course, they are kind of may run into each other, but when they combine, then you have a new shock of size z1 plus z2. So you have some kind of coagulation type behavior when clusters of different sizes combine to form a larger size. Okay, so now okay, so let me make the fifth remark. Now, I was planning to make 2 remarks, and I couldn't remember the second remark, and now nobody can stop me. The fifth remark that I want to make is that it turns out that if you start with a Markov process that is not Leve, namely you make a jump, but the statistics of the jump is not just a function of the jump size. It may depend on rho minus and rho plus. As we will see later, this picture still persists, though if you start with Leve, it may not stay Leve. I'm sorry. If you start with Leve, it stays Leve, but if you start with arbitrary, OK, maybe I make this remark. So if instead of burgers, we consider this equation. With h some nonlinear function. Some say convex function.
So why is the first equation equal to 0?
Say it again.
The first equation.
Sorry. Thank you. So let's, I can blame everything on my jet lag. OK, so if instead of burgers, we consider this equation with h, which is some convex function. Now, as we will see later, if you start with Leve, rho at later time is still a Markov process, but it's not going to stay Leve unless h is quadratic. Is going to be a Markov process, though for h which is not quadratic, h which is not quadratic, rho t may not be Leve. So Berger's equation is a kind of a good log that Leve stays Leve. If you switch to non-Berger's equation, then the Leve property would not survive. Okay, so kind of a warm-up of things that are coming up. So that's the first set of classical results that you can say about the Berger's equation that is rather well understood when the initial condition is random. Now, the second example, as our second classical result, consider an initial data that is white noise. Consider Berger's equation. But now this time initial condition is white noise. Now here it's not clear how to interpret this, because white noise, do I have positive jumps or negative jumps? It's not clear. Of course, you expect to have positives and negatives. So this somehow may not appear to be compatible with the previous discussion we had. Because previous discussion, we had the Leve of only positive jumps. Here, I'm just starting with white noise. First, what do I mean by a solution to this equation? Alternatively, you may start with the integrated version of this, which is the Hamilton-Jacobi equation. So you start with Hamilton-Jacobi equation for which the initial condition is Brownian motion. By this, we mean rho is ux, where u solves ut equals 1/2 of ux squared, the so-called iconal equation, and ux0 is Brownian motion. But by Brownian motion, what I mean is that u at the origin is 0, on the right is a Brownian motion, on the left is Brownian motion. They are independent from each other. So it's just two-sided Brownian motion. So here we mean u0, 0 is 0, and ux0 for x plus minus bigger than 0 are two independent standard Brownian motions. Okay. So something very interesting happens, and what we get at later time now is going to be a Leve process again. So this kind of white noise disappears, and you have a reasonable process. And you can derive very precise formula for the jump kernel. So now comes to spelling. I think it's spelled something like this, or a variant of this. I might be able to find that somewhere in references I brought. Maybe it's here. Of course, I expect people to remember my name, and then I mess up everybody else's name. It's kind of embarrassing. There's E missing. Okay, so let me call this equation 2. Let rho be as 2. Then x going to rho xt for t positive is a Leve process. And this Leve process would have a decreasing drift and a jump measure. And the jump measure can be calculated explicitly and expressed in terms of the so-called Airy function. I'm not going to write it down because the formula is rather messy, but would be a Leve process with a decreasing, with a negative drift. And a jump kernel that can be expressed explicitly. Actually, not very explicitly. I mean, it satisfies some equation involving the Airy function in terms of so it's kind of rather a surprising fact, but it is also true. And Say it again. Yes, and it's going to be with only negative jumps. Positive jumps, because I wrote it differently. It's going to have only positive jumps. Would be a jump kernel that can be expressed. It has only positive jumps. So kind of rather surprising. Needless to say that the jump kernel blows up as t approaches 0 because you converge to white noise. But nonetheless, something like this happens. So let me summarize some of the things we've seen so far. That's right. Absolutely. The law is translation invariant. Oh, yes. That's right. The kernel doesn't depend on space, the jump kernel. It doesn't matter where you are. You make the same stochastic jump. So moral, what we learn is that in the case of Berger's equation, Leve processes play a prominent role for the stochastic Markovian solutions. So that's what we learned. Somehow Leve processes would be very important. Now, can we go beyond Berger's equation? This is the next question I want to address. So that's the next thing I want to address. Yes? Hamilton-Jacobi. For Hamilton-Jacobi equation. Oh, you see, you can always, for any Hamilton-Jacobi, you can formulate, if it's convex, you can always formulate, and you know, it just, the initial data happen to be Brownian motion. Yes, I mean, for any convex Hamilton-Jacobi, for any Hamilton-Jacobi convex flux function, there's a control. No special about, just initial data. So the dynamics is not random or anything special, just initial data happen to be a Brownian motion. Okay, you know, in fact, the way Bertoine proved his theorem used very much a control theory formulation. Though later I'm going to kind of relax and forget about that type of approach. However, the original proof of Bertoine relies on the variational formula. He basically derived the law of the minimizer in this variational problem. That would be a monotone, because if there's a minimization problem, if there's some parameter y that you have to minimize it, y would be a function of x and t. So for each x and t, you have the minimizer in the variational problem. That yxt as a function of x is going to be a Leve process, a monotone one, because the minimizer is going to enjoy some monotonicity. And you know, then he derived a law for the minimizer, in fact. And once you have a formula for the minimizer, then you can easily translate it to a formula for the density rho. That's right. However, later on, I'm going to just kind of avoid that variational formula and try to look at the problem directly. Okay, now the question is, can we go beyond Berger's equation? Is there any chance to have a theorem of this sort? And the general theme is that roughly, if rho t equals h rho x, and rho x0 is, say, rho 0 x, and this is a suitable Markov process. With positive jumps only. Actually, I don't need positive jumps. So I'm not, in fact, the general theme is that if you look at this equation, and H could be convex or concave or mixture of the two, but so long as you consider a scenario with no rarefaction type discontinuities, then this Markov property survives at later times. So Markov process with no rarefaction type discontinuity ut, then this picture persists at later time. So that would be the general thing. And this kind of principle was formulated as a conjecture by Govind Menon and Ravi Srinivasan. I guess you can correct my pronunciation if I didn't say it right. So that would be Menon and Srinivasan. So that would be the general principle, that you can start with a Markovian initial data, and so long as you don't have any rarefaction waves, then you can derive an equation. Though the important thing is that if H is not quadratic, then you have to forget about Leve processes. Even if you start with Leve process, at later time would not be a Leve process. So, and therefore, all that equation you had for the Leve exponents would be irrelevant. But what would the type of things that you want to keep track of would be the corresponding jump measure. You can derive a very precise equation for the jump measure now. Now, as a warm-up, so before I state the conjecture and make various comments, let me consider the following scenario. So imagine that rho t equals h rho x, and rho x0 equals rho 0 x, where I want to think of rho 0 x as a solution of some ODE. With imagine that rho 0 x, when differentiated with respect to x, equals to a suitable b0 rho 0 x for a suitable function b0 from R to R. So it's as if in order to determine what the initial data is, I solve some ODE. For example, imagine you solve this ODE for x positive, and you just concentrate on x positive, and let's say that there's some initial data. So rho 0 at 0 is some A. So imagine that initially, some B0 is given, and I start from position A, then I solve some ODE. That would give me a suitable profile. And the velocity of the ODE, or the vector field of ODE, is this given function B0. So imagine B0 is given initially. And imagine that this picture persists at later time, meaning at later time you have a solution to ODE for which B0 is replaced by a new vector field that depends on time. So imagine that at later times, we have a similar picture. Of course, I can also solve this ODE for negative time. So we have some profile that is defined for all x's. So here, x plays the role of time in ODE somehow. Not be confused with t. Okay? So imagine the same thing is true at later time. Namely, if you differentiate rho with respect to spatial variable, then there would be a function b for which this is true. For a suitable function b rho t. Okay? Can I derive? So this is kind of a baby version of the type of problem we have in mind. A solution to ODE can be regarded as a Markov process with no randomness in it. And then if I insist that there is no noise in the kind of dynamics I have, then I always have some ODE to solve. And now my job would be to derive an equation for the evolution of bxt as a function of time, with initial data bxt equals 0 equals b0. So we wish to derive an equation and it's easy to derive, if such thing is possible, it's easy to derive such an equation. Indeed, okay, so I have this equation. Indeed, in short, we have, if I summarize the situation, I have one equation, so I make an ansatz. Suppose this is true, that if initially, for any initial data, I can imagine that such b0 would exist. Imagine that I just come up with some b0 for which this is true. Then I assume solution is smooth. I can do all the usual manipulation. I can do calculus. And then at later time, you have this equation. I want to derive some equation for b. Quite a natural question. And so basically, we have two equations to keep in mind. Is that rho differential with respect to time equals b of rho t. That's one equation. And this equation itself, remember, this is h prime of rho x. If rho x, well, I'm sorry, this is rho x. So rho differential with respect to x is given by b of rho. And rho differential with respect to time is given by h prime of rho x. But since rho x is b, is h prime rho b rho t. So I have these two equations, and I just have to make sure these two are compatible. The compatibility of these two equations would give me the desired equation for b. Just the fact that the order of differentiation would not matter. So I'm going to differentiate this with respect to t and differentiate this with respect to x, match them. That will give me the desired equation for b. Okay? And this implies okay, so this implies, let's look at rho xt. Differentiate the first equation with respect to time. That would give me bt plus b differential with respect to rho times rho t. But rho t is given by the second equation. So that would be h prime of rho times b. That's what I get if I differentiate the first equation with respect to time and use the fact that rho t is h prime of rho times b. If I differentiate the second equation with respect to x now, I would get h double prime of rho times rho differential respect to x, but that is b. That b times the other b would yield b squared. And then if I differentiate b, I would get h prime of rho times b differential respect to x. Let's see. I'm differential respect to x, so I have b rho times rho x, which is b again. All right? You get something like this. Since they have to match, then I have the equation bt equals. So if this is true, and if you have classical solutions, then the time derivative of the vector field b is given by the second derivative of h times b squared. Let's, for example, assume h is convex. Then this would be positive. So I have bt equals something positive times b squared. Okay? So this looks nice. Then you may wonder why we bother with studying conservation laws when you can kind of reduce it to an ODE of this type. Well, the thing is, you may have blow up in this equation because of quadratic b squared. If this guy is uniformly positive, and if you start with b that is sometimes positive, then in finite time you may have blow up. And that's not surprising at all, because you expect to have discontinuity no matter how small the initial data is. You expect to have discontinuity that if I translate it to this picture, the discontinuity has to do with the fact that the space derivative of rho may blow up, and that would be the same phenomenon as b blowing up. So note that if h is nonlinear, then the equation of 3, then a 3 may have a blow up. This is compatible with the occurrence of shocks at later times. So that's not surprising. But let's make the following observation, and that is, however, for example, when h is convex, the second derivative is positive, and if the initial b is sometimes positive, so is the increase of rho. So if you look at the initial data, if you have, there are two possibilities. If you have b0, which is always negative, if b0 is always negative, that means the initial data to this equation is negative. And if this guy is positive, then the negativity persists at later times, and there would be no shock discontinuity. So if you have an initial profile that is always decreasing, I don't have to worry about shocks. But if you have something that sometimes increases, then I have to worry about entropy, which is a kind of well-known phenomenon if you use the method of characteristics to study the solution to that equation. And b0 is sometimes positive, then you may have blow up in finite time. So in summary, there are two things can happen. If b0 is always negative, then there is no shocks. And this would give you all information you need. The solution regarded, the profile regarded as solution to an ODE would come from a vector field B that comes from solving this equation. So that case is clear. No shocks, and 3 would give us B at later times. This B can be used to fully determine rho at later times. However, if B0 is positive for some x's, then the theory of entropy solutions come into the game. Then we need to use the notion of entropy solution to kind of deal with the blow up, to resolve the blow up. Okay. The picture is very clear. Now imagine that I start with a situation like this, for example, or if you start with this solution, then whatever I say works only for finite time until that ODE blows up. Okay. Imagine I start with this, and then I insert discontinuities, but this time in a random fashion. Then you hope that this picture persists at later times. That would be. OK, so you give me some B0. This is a function of rho. I solve this ODE as a function of rho. So I produce a function B rho t. Then when I have B rho t, then I have to solve the corresponding ODE. Is that what you mean? No. This is a function of, so B here is B of rho t. Rho is the argument, is the dummy variable in this problem. You give me h, which is the flux, differentiated. Then I have the second derivative of h. You see, I'm solving this ODE as a function of rho and t. You see, here also, x is the parameter of the solution to the ODE. But B0 is a function of rho only. So again, initially, you give me a function B0 of rho. Then I solve this ODE for B as a function of rho and t. Make sense? Is it still confusing? I'm playing with characteristic equations. This is the characteristic equation in disguise. Absolutely. But it's very instructive because, you know, what I'm looking here. You give me some initial data for which I assume is either Markov process or the baby version of it would be a solution to an ODE. And I want to kind of evolve the ODE. Instead of solving the PDE, I want to evolve the ODE, the parameters of ODEs. Make sense? Stefano doesn't look happy. You know, we are old friends. I remember when we first met. I think that was 30 years ago. No, I should not reveal, you know, this kind of thing. More than 30. I think when did you come to Quran? 1980? Yeah, 30 years ago. Wow, 30 years. We have to celebrate, 30 years. So I'm going to say the nice theorem just for you. This is your gift. OK, so is this picture clear? So if the rho 0 is a decreasing profile, you kind of imagine this decreasing profile is a solution to some ODE associated with B0. Then you start with B0. So this should be solved with initial condition B rho 0 equals B0 rho, right? You solve this ODE, take the solution to this ODE, and then solve another ODE, but now the parameter is x. So there are kind of different ODEs. One is an ODE for rho. The other one is an ODE for b. B is a function of rho. That's why the confusion happens. OK, so now so after understanding this simple scenario, now I want to make things more complicated. Now next, I just realized that in this room, I know many people for more than 30, almost 30 years. It's not just Stefano. Maybe 1/3 of the audience or something. OK, next, imagine that initially, x going to rho 0 x. So now I want to start with this profile, x going to rho 0. I want to think of rho 0 x as a random process now. Previously, I was thinking of it as a solution to some ODE, but now I want to think of it as a random process. And this random process is going to have an infinitesimal generator. There is a drift part that is associated with this rho 0 that I just erased, and then there's a so in other words, instead of taking solution to the ODE, I want to insert random jumps in between. So it's as if you constantly want to solve the ODE, but once in a while a clock rings, and then you make a jump. And then you continue solving the ODE, a clock rings, continue. I want to have a picture like this. That would be a generalization of what we had. So initially is a Markov process with infinitesimal generator given by this. So infinitesimal generator, that means I have to give you some L0. L0 means the infinitesimal generator of initial data. So that guy is acting on functions of rho. So rho, so x is the time here, and rho is the value of the process. So rho 0x is a random process for which x is the time parameter. And I want to tell you what the infinitesimal generator is. So I want to have ODE plus random jumps. The ODE part would be a first-order differential operator. And the drift of the ODE would be the coefficient of the first-order term. So it would be B0 rho times H prime at rho. So this part, if I only had the ODE part, this part does represent the ODE dynamics. But I want to kind of add to this a jump. And I want to make sure that I only have positive jumps. So I'm going to start from rho. And that means rho at some point decides to make a jump, a positive jump. That's why the integral goes from rho to plus infinity of h switching to new state from rho at some random location x. And I want this to happen with a suitable kernel that I denoted by F0 rho d rho star. So this basically, in other words, x going to rho 0 x is a solution to an ODE of the form plus a random jump and the total integral of this kernel basically tells me how far I have to wait to make that jump. The integral so this is a kernel. The total mass of the kernel the kernel, this measure is concentrated on the interval rho infinity. Its total mass has to do with the mean of the waiting time. But when I say time, by time what I mean x. That means how far rho 0 has to wait in order to make that jump. Is how far to go before jump. And this f rho d rho star lambda rho, the normalized version of this is the statistics of the jump. That would be the probability to jump from rho to rho star. So if we want to draw a picture, so this is rho 0. Let's start with some A. Basically, for the scalar conservation law, you may solve it with a boundary condition. I may solve it only for positive x's, provided I tell you what's happening at position x equals 0. So basically, I do some ODE here with, say, B0 negative or non-positive. But then I decide to make a jump. This jump would be random. That would be my rho plus. You make a random jump. The weighting depends on what the state of the solution to ODE is. You have to integrate this over this interval to know what's the probability of not observing any jump in that interval. But once you do observe, then you suddenly change the value, and then you solve the ODE again, but now with new initial data. Then you continue, the clock rings, you do this, so on and so forth. So I want to have a picture like this initially, which is, again, is basically ODE, the deterministic ODE plus some jumps in between. Now, the Menon-Srinivasan conjecture says that this picture persists at later times, and you can derive an equation for the evolution of the kernel. So forget about the characteristic equation. You really focus only on the kernel, and you can derive an equation. And also, this evolves, but it's easy to derive an equation for this guy because the equation is already given here. That would be the corresponding dynamics for the coefficient. So conjecture, which is kind of no longer a conjecture because now we know how to prove it, but the conjecture of Menon and Srinivasan. This picture persists at later times. So this is the rough statement of the conjecture. But now I want to give you more details. Now you have to derive an equation. You already have an evolution for the drift, but you want to derive an equation for the law, the statistics of jumps. And how you can derive an evolution, at least formally, and that requires some calculation. But more precisely, if you look at x going to rho xt, is also a Markov process. So more precisely, for fixed t, and I want to tell you, I want to write down an infinitesimal generator. With generator, now the generator, so somehow as if generators are evolving. So initially you have this infinitesimal generator, though the generator is very simple, consists of a drift and a jump kernel. So this evolves to a new generator, which has a drift part and okay. Now, with B solving bt equals second derivative of rho times b squared, and F satisfies some ODE. So this would be an ODE in space of kernels. And it kind of takes time to write down what that evolution is. But for one thing, this is some kind of has the same flavor as a Smoluchowski equation, as I mentioned before. So it would be some kind of kinetic equation. Though a Smoluchowski equation has to do with clusters of different sizes combined to form a larger cluster. So you have a cluster of size Z1 and Z2. They combine to form a cluster of size Z1 plus Z2. Here, as I mentioned, Leve does not stay Leve in general. So you're not going to have a kind of evolution equation or some kind of coagulation evolution for the cluster sizes. There is no size. You really need an evolution for a pair, rho 1 and rho 2, combined with another pair, rho 2 and rho 3, to form a new pair, rho 1 and rho 3, and two jumps combined. So you have to write an equation for that. And F rho d rho star t solving a kinetic type equation that in some sense has the same flavor, that somewhat reminds us of a Smoluchowski equation. And again, I haven't written it down yet, but eventually I'm going to give you a formula. The formula is going to be rather involved. Okay? Maybe is it? Yes. Actually, F will depend on B, and that's why the equation is pretty involved, because there would be various terms. One of them is really kinetic, purely kinetic when things combine. But then since these guys, the state on the left and the right, they evolve with space also, with speed given by B, of course, the evolution of F depends on B. B itself, you can calculate it with no reference to F at all. But F, you need to know what B is. First, you solve B from the first equation, and you insert it in the second equation to determine F. Okay, so that would be done. Yes? Of course. That's the whole idea. Would be the entropy. That's why I need the condition that H is convex. In fact, I'm going to write an equation that makes sense no matter what. But if H is convex, that would be entropy solution. And tell you exactly what's going on. So what's happening is that the type of equation you derive is always for a jump that goes from some rho to something larger. If H is convex, that is compatible with the entropy condition. You can always solve it, but what you get is not going to be entropy condition unless H is convex. Yes? That's a very good question. You see, that's something that I've been looking at, but with no success. Not so much this equation, but you want to add to this some external force. If you add an external force, that will kind of balance all these jumps. And that actually brings us a series of theorems that are available. But not a la this calculation with kind of different methods. Goes back to the work of Sinine, E, I forgot a couple other names, and recent works. When you have an external force, now it depends on the form of the external force. If the external force, it's periodic in space and Brownian motion, that goes back to the work of Sinai and the others. And recently, they managed to do the case when you have randomness in space variable also. But it's quite plausible that using this method, you can kind of get that theorem in certain cases. In fact, provided the invariant measure itself is a Markov process. So then this would be the way to go. In fact, that's one of the original reasons that I looked at this equation. The other reason that I had in mind was hopefully eventually I get to Carter-Parisi-Zhang equation. Because in fact, the case for which you have initial data that is white noise, when you look at the explicit formula for the kernel, it kind of involves Airy function, which reminds some of the exact solution of Carter-Parisi-Zhang equation. So this, of course, is not Carter-Parisi-Zhang because you need to add a second order term on white noise. But if you forget about the second term and you have white noise only, then there are some conjectures that I'm going to formulate later. More questions? So, I'm from Iran, and the way we finish a story is that we never finish it. We, get to a point when, the exciting part would be for the next story. You know about the 1001 Nights. So I think this is an ideal place to finish. The most important part is this. But if you want to know what that equation is, you have to come tomorrow.